Our second lecture on the kinetic theory of gases is going to be focusing on the ideal gas law. In our first section, we talked about the initial conversions of pressure, talked about your basic gas laws, Boyle's, Charles, Gay-Lussac's, combined, and Avogadro's law. Now we're going to focus on the ideal gas law, which allows us to compare pressures, volumes, temperatures, and the number of moles together at one time. An ideal gas is defined as an imaginary gas that conforms perfectly to the tenets of the kinetic molecular theory. You're able to abbreviate the kinetic molecular theory as KMT. We can look at the initial relationships that we had between the different variables, pressure, volume, temperature, and the number of moles, and combine them together into one law. From our last lecture, we know that volume and temperature are directly proportional at a constant pressure and number of moles. We know that volume was directly proportional to the number of moles when we had a constant temperature and pressure. And we knew that volume and pressure were inversely proportional to each other when we had a constant temperature and number of moles. When we combine all of these relationships into one equation, we get the PV equals nRT equation. The R is what we call the universal gas constant, and we will look further in just a minute about the different values that we can have for R in these problems. Now when we look at the universal gas constant, the value for R is dependent on the unit of pressure that is given in the problem. The rearranged equation to solve for R would be R equals PV over NT. When we use the different pressure units at STP conditions, we can obtain the following values. So when we look first at our R in atmospheres, that would give us 1 atmosphere for the standard pressure. The standard volume for 1 mole of a gas is 22.4 liters. So I'd have 22.4 liters. And then I would divide that by 1 mole. And 0 degrees Celsius would be 273 Kelvin. So our R value would not have any units cancel. That's its purpose, is to cancel off the units that we would have for all of the others except what we're trying to solve for. So my value would be, in this case, 0.082. It's technically 0.6, but we can just round it to 1, and we would have liter atmospheres per mole Kelvin. When we look at the R value in terms of kilopascals, instead of using 101 for the for the 1 atmosphere, we're going to use 101.325 for the kilopascals, and we would still multiply that times the 22.4 liters, dividing it by 1 mole and 273 Kelvin. When we do that, we would get an R value of 8.314 liter kilopascals per mole Kelvin. And finally, if we have either millimeters of mercury or torr as our value, we know that we have 760 millimeters of mercury or torr, still using the 22.4 liters. 1 mole and 273 Kelvin. And if we do that, it's 62.36, but we're going to round it to 62.4, and that would be liters times millimeters of mercury per mole Kelvin. So I just want you to take a moment and notice that when we set this up, every other variable, volume, temperature, and moles, are the same throughout each one of these different R values. Only the value for the pressure changes, and we would use one of these to just simply cancel off whatever given unit of pressure we have. If you'd like, you can just simply memorize the 0.0821 for your atmospheres, and then just convert whatever the given pressure is, whether it's millimeters of mercury or kilopascals, just simply convert those into atmospheres, and then use that 1 R value to solve the problem. Either way you can do it, and you'll still get the right answer. Let's now look at an example problem. An automobile tire at 23 degrees Celsius with an internal volume of 25 liters is filled with air to a total pressure of 3.18 atmospheres. Determine the total moles of air in the tire. So in this particular instance, please remember you always have to convert your temperatures into your Kelvin temperature. So I'm going to add 273, so that would make that 296 K. So I have my pressure times the volume divided by the R and the T will equal N. So in this particular case, I have 3.18 atmospheres. I have 25.0 liters, 273 Kelvin, and for the R value, because it is in ATMs, I'm going to use the 0.0821 liter atmospheres per mole Kelvin. So it should cancel all units except for the last one that we're trying to solve for. So notice I have liters in the denominator, liters in the numerator, atmospheres in the numerator and the denominator, and finally the Kelvin in the denominator that are canceling, and that leaves me with an answer of 3.27, and you would see 1 over 1 over moles for the unit. So we would just take, any time we divide 1 by a fraction, it's the reciprocal, so that would just leave me with 3.27 moles as my final answer. Remember, with significant figures, because we're adding, we go to the ones place for the 23 degrees Celsius. So I'd have 296, which would have 3 significant figures. I should have wrote that in wrong. That'd be 296, 3 significant figures, 3 significant figures, 3 significant figures. So my answer would have 3 significant figures. We're now going to look at some derivations of the ideal gas law, basically solving for something other than moles within a problem. So you can always use the ideal gas law and then just do the stoichiometry after that to determine the number of grams or moles, or you can use some of these shortcut formulas that I'm about to show you to help you out. So as we begin this process, we're going to first look at the ideal gas law where we are involving molar mass. So anytime you have a mass or a molar mass, you are able to use this derivation. The original mole equation that we had, the number of moles equals the mass divided by the molar mass. We're symbolizing the N as your number of moles, the mass M, and the molar mass as just a capital M. So when we substitute this into our equation where I have the N and the PV equals nRT, I'm going to replace that with the little m over capital M times RT. So if we want to multiply both sides by m to get everything into the numerator, this will give us an equation of MPV equals little m RT. So the first little thing that I told you guys, I was going to give you in class a couple of shortcut ways to help you memorize these equations. For those people who are not at Johns Creek, you can rearrange this equation just a little bit and say MRT equals MVP, and you can just remember that from like the old character on the A-Team, Mr. T. You could have Mr. T is the MVP, so you can remember it that way. For all of our Johns Creek people who are very much the mathifites, you can think about your revered calculus teacher, Miss Meert, and you could say that Meert is MVP for the math program. And that would be an easy way to remember this equation as well. So that is the first little shortcut that you guys can use to help you remember this equation. Let's look at another example. In this example, it asks what is the pressure in a 304 liter tank that contains 5.67 kilograms of helium at 25 degrees Celsius. So the first thing we need to do is convert our mass into grams. So I'm going to take the 5.67 kilograms and we can say 5.670 kilograms 1 kilogram, 1,000 grams. So I'd have 5,670 grams of helium. The molar mass of helium, so that would be my little m. My capital M for the molar mass would be 4.00 grams per mole. And you'll notice in this question, it just says what is the pressure. It doesn't tell us what unit to solve it in, so we can choose whichever one that we would like. So I'm just going to, in this case, go ahead and solve for the pressure in atmospheres, and we'll plug in our values and solve the problem. So my molar mass, 4.00 grams per mole. My pressure is what we're solving for, and then we have a volume, 304.0 liters, and that is equal to the mass, 5,670 grams, the R value, 0.0821 liter atmospheres per mole Kelvin, and then the temperature, 25 plus 273, that will be 298 Kelvin. So to solve for P, I'm going to divide both sides by 4.0 grams per mole and also 304.0 liters. So you'll notice again, liters cancel. I have moles in the denominator for those fractions, so they will cancel. I have Kelvin and the Kelvin canceling out, and grams canceling out. So all I have left will be the atmospheres. So when I plug that in, I get 114.1. However, with the 298 having only 3 significant figures, we would have 114, not liters, but ATMs for our final answer. So I wanted to show you guys just a couple more example problems where you will see different units of pressure involved. So for our first practice question, we have at 28 degrees Celsius and 725 millimeters of mercury, 750 milliliters of an unidentified gas has a mass of 3.90 grams. What is the molar mass of the gas? So the first thing, I'm going to convert my temperature into Kelvin. So that would be 301.0 Kelvin. And 750 milliliters, because the R value is given to you in liters, we have to convert the milliliters into liters so that the unit can cancel. So I'm going to divide this by 1,000. So that would give me 0.750 liters. With all the other gas laws, Boyle's law, Charles' law, Avogadro's law, it doesn't matter what the unit of volume is, but because of the fact that the R value has those units, we must have proper units for cancellation. So as we set up our problem here, again, I'm solving for molar mass, so I'm looking for M. So I would take the little m times RT divided by P and V. So my molar mass would be equal to 3.90 grams. In this case, because I have the 725 millimeters of mercury, the R value that I will use will be the 62.4 liters times the millimeters of mercury per mole Kelvin. And I would have my temperature 301.0 Kelvin. And now we can divide that by 725 millimeters of mercury, and my volume, 0.750 liters. So our molar mass for the first problem would be equal to 134.7. We have millimeters of mercury cancel, we have Kelvin cancel, we have liters cancel, and I'm left with grams per mole, which should make sense for our molar mass. So doing that with significant figures, we'd have 135 grams per mole. All right, so let's look at a second problem now involving kilopascals. So what volume will 545 grams of hydrogen gas occupy at 26.0 degrees Celsius and 185 Kelvin? So please remember, since I have a substance given, I have the mass of it, but I also have its identity, so I know its molar mass as well. So hydrogen gas would simply be H2. So I can set this up again with solving for volume. So I'd have little m RT over m and p. So I can do 545 grams. I now have an R value because it's in kilopascals of 8.314 liter kilopascals per mole Kelvin, and I have a temperature 26 degrees Celsius. That would be 299.0 Kelvin, and I can take all of that and divide it by the molar mass of hydrogen, 2.02 grams per mole, and the pressure, 185 kilopascals. So kilopascals would cancel, my moles would cancel, Kelvin would cancel, and my grams would cancel, leaving me with liters, which makes sense for volume. So my volume with three significant figures, we would have 3,630 liters of hydrogen gas. Okay, so let's finish up with a couple of practice problems here. So we have, what mass of sulfur dioxide will exert a pressure of 125 kilopascals at a volume of 32.5 liters and a temperature of 32 degrees Celsius. So in this first problem, we would take the 125 kPas. We have a volume of 32.5 liters, and we have a molar mass of sulfur dioxide, again SO2, that would be 64.06 grams per mole, and that is going to be equal to the mass, which we're solving for. Because we have kilopascals, we're going to use the 8.314 kilopascals times liters per mole Kelvin times the temperature, 32 degrees, plus 273 would be 305 Kelvin. So I'm going to take each of these numbers and divide both sides by the 8.314 and the 305 Kelvin. So that should be 305.0. Add that in. There we go. So again, the Kelvin cancel, the kilopascals cancel, the liters cancel, and the moles cancel. So that will leave me just with mass. So I have just the grams from the numerator. So when I plug all of that in, I have a mass of 102.6, and we only have three significant figures, so we'll say that will be 103 grams of SO2. Alright, so for our next problem, we have 2.94 grams of a gas exerts a pressure of 0.284 atmospheres in a 3.6 liter container at 265. Calculate the molar mass of the gas. So for this problem, again, I have my little mass, 2.94 grams. We're going to multiply that times 0.0821. Again, since I have atmospheres as my pressure unit, I have liter atmospheres per mole Kelvin. And I also have the temperature, 265 plus the 273. That will be equal to 538 Kelvin. And I can now divide this by the 3.60 liters and by the pressure, 0.284 atmospheres. So atmospheres, liters, Kelvin, and that leaves me with grams per mole for the molar mass. And the molar mass will end up being 127 grams per mole. The second derivation of the ideal gas law is density. And in order to get density, we're going to do the same manipulation that we started with for molar mass. So we're going to take the mole equation and convert it into mass divided by molar mass. And we remember, hopefully, that the density equation is equal to mass divided by volume. So what we need to do is substitute the m over m, capital M, for the n in the PV equals nRT. And once we have that, we're going to divide both sides by V. And hopefully you notice we have m over V now, which we can substitute the d in for the m over v, and that leaves us with an equation of Pm equals dRT. So as I said, I have a number of different ways to help you guys remember this. This next one I can't take credit for totally. I had some girls at one of my previous schools that always like to use phonetics to help them memorize their formulas, and so they thought of PV equals nRT as pervnert, and that got me thinking in the lines of pervnerts. Sounds very similar to pervert. And so if we just do a little creative rearrangement of this equation, we can say that your pervnerts get dirty, dRT, in the PM. So there's another way to memorize these equations. Pervnerts get dirty in the PM. So as an example problem, let's determine the density of F2 at STP. Now, in this type of situation, we're going to solve for it in grams per liter. Remember, every time that we see STP, that gives us two values, 1 atmosphere and 273 Kelvin. It's completely your choice how you want to approach this problem in terms of pressure, but you can use either atmospheres, kilopascals, or millimeters of mercury. You just have to change your R value that's associated with it. Personally, because it's just 1 atmosphere for the pressure, I would use it as you solve this problem. So I'm going to take my dRT equals PM. I'm going to divide both sides by R and T. So when I look at my numbers, I would have 1.00 atmospheres. I would have the molar mass of fluorine, again 2 times 19, since it's diatomic. So I'd have 38.00 grams per mole. And then I would divide the molar mass by the R value, which we know is 0.0821 liter atmospheres per mole Kelvin, and by our temperature of 273 K. So as I look at this, my moles would cancel, my Kelvin cancel, my atmospheres cancel, and I'm left with grams per mole. So makes sense for, or grams per liter, excuse me. So that makes sense for the density. So if I plug my values in, I have 38 divided by 0.0821 and divided by 273, and that gives us a density of 1.695. So let's change that to 1.70 grams per liter. Now, in this one particular case where we have it occurring at STP, we also know that 1 mole of a gas equals 22.4 liters. So there's one other way that we could go about solving this, only in this one particular situation. So instead of using the density equation, we could simply take the mass, which in this case would be our molar mass, and we could divide it by the volume, which we know would be the 22.4 liters, because molar mass is defined as the number of grams found in 1 mole, and the volume is 22.4 liters for every 1 mole of a substance. We could just simply take the 38.00 grams per mole, divide it by 22.4 liters for every mole. Notice the moles would cancel, and I'll be left with grams per liter. And if you do 38 divided by 22.4, guess what? It'll still come out to equal 1.70 grams per liter. So either way you want to do it, but you can only do this second little shortcut here when it's at STP. So only at STP. So our last concept will be dealing with gas stoichiometry. So we're dealing with non-ideal conditions, i.e. not having conditions of STP. So when you have the conditions that are not 273 Kelvin or 0 degrees Celsius and 1 atmosphere of pressure or any of its equivalents, we have to use the ideal gas law to determine the number of moles of the gas and then apply that to the chemical reaction stoichiometry. Or you could have enough information given to you within the problem to start off with the stoichiometry to solve for moles of the gas and then apply it into the ideal gas law at the end. So you have to decide based on the information that is given to you in the problem whether you need to use the PV equals nRT first or second within your problem. So let's look at an example problem for a gas stoichiometry question. So we have molten potassium chlorate reacts explosively with sucrose by the reaction 8KClO3 plus C12H22O11 forms 8KCl plus 12CO2 plus 11H2O. Calculate the volume in liters of carbon dioxide gas produced when a 2.35 gram sample of sucrose reacts with excess potassium chlorate at 25 degrees Celsius and 0.950 atmospheres. So when you're solving these problems, as I was trying to indicate in the previous slide, what you want to do is look at the information. We know that since it's 25 degrees Celsius and 0.95 atmospheres, it is not at STP conditions, so I cannot just simply convert to volume by using 22.4. If it is at STP conditions, then you can do your normal stoichiometry and just use 22.4 liters. Now, in this case, what you want to do then, after you've identified the fact that it is a non-ideal gas problem, you want to look and see, do I have enough information initially to plug in to the PV equals nRT equation and be able to solve? So in this case, because I'm looking for volume, I do not have moles of CO2, but I do have temperature and pressure. So as a result, I'm going to have to start first by using the normal stoichiometry, and then second use the PV equals nRT. So I do have grams, but notice that the grams is for sucrose, not for the CO2. So I need to convert from the sucrose into the grams or the moles of the CO2 when I solve this problem. So the first thing, I would take the 2.35 grams of the C12H22O11 converted into moles. So 1 mole of the sucrose is 342.34 grams. C12H22O11. I have a 1 mole of C12H22O11 to 12 moles of CO2. And at this point, I can now solve. And when I get that, I'm going to end up with 0.0823 moles of CO2. So now that can be my value for N. So I have PT and V and N, so I can solve for V. So now, as a second step in that process, this being the first, now for the second step, I have PV equals nRT, so I can divide both sides by P. So I have 0.0823 for my number of moles. Since I have atmospheres, I have 0.0821 liter atmospheres per mole Kelvin. And I have the temperature, 25 plus 273, actually that's 298.00 for the Kelvin temperature, and I can now divide that by the pressure, 0.950 atm. So once more, atms cancel, moles cancel, Kelvin cancel, and I'm left with volume in liters, and I end up with 2.12 liters of CO2. So for our next example problem, it says when heated, NH4NO3 decomposes into H2O and N2O, both gases. What mass of NH4NO3, ammonium nitrate, must have reacted to produce 30 liters of gas at 273 Kelvin and 760 torr? So please notice in this it says of gas. I have two different gaseous products. So what we can do with that is when we get to the mole ratio, because we're just going from the liters into moles, the identity of the substances is not important, so I can just simply add my coefficients together. But one thing I want you to notice, again, we need to determine if this is ideal or non-ideal conditions. So notice I have 273, that one would be a check mark. 760, that is the equivalent of 1 atmosphere. So in this case, I do end up having ideal conditions. So I can just use typical stoichiometry to solve this problem. So I could take the 30.0 liters of the gas, and I know that there will be 22.4 liters of the gas in 1 mole of the gas. And now I can say that I have 3 moles of the gas, again 2 moles of the water plus 1 of the N2O, dinitrogen monoxide, and I have 1 mole of the ammonium nitrate. So I can convert into the moles of ammonium nitrate, and then the molar mass to get us into mass. 1 mole of the ammonium nitrate will be the equivalent of 80.06 grams of the NH4NO3. So when I plug that in and solve, 3 significant figures due to the 30.0, we end with 35.7 grams of ammonium nitrate. So we're going to look at one last problem. So I figured since we are dealing with stoichiometry, what better way to do a stoichiometry problem than to end it on a limiting reactant. So as a beginning part, we have an equation of Al plus HCl forming AlCl3 and H2. So I'm going to balance that by placing a 2 and a 6 a 2, and a 3. So you'll notice we're starting with 10.7 grams of aluminum and 42.5 for my grams of HCl. So I'm going to give us a little practice using our rice tables. Yay! So I'm going to divide this initially by 26.98 grams for its molar mass, and I'm going to divide the 42.5 by 36.46 grams per mole for the molar mass of hydrochloric acid. So when we get this divided out, we have for our initial number of moles 0.397 for our moles of aluminum, and we have 1.17 for our moles of HCl. I have a coefficient of 2, so I'd have minus 2x for the aluminum, and I have a coefficient of 6, so I have minus 6x for the hydrochloric acid. And we're trying to solve for volume, so my initial amount of volume of H2 gas is 0, and that would just be plus 3x. So now to figure out my limiting reactant, again, we're going to set each of these initial ones equal to 0 to see which one has the smaller x. So again, we're taking I minus C equals the E. So I have 0.397 for my moles minus 2x equals 0. So I can add 2x to both sides and divide by 2. And my x value that we would get would be 0.198 moles. And for this equation on the hydrochloric acid, I have 1.17 minus 6x equals 0. So in this case, my x would be equal to 0.194 moles. So the hydrochloric acid, that would in this case be my limiting reactant. So I know I can take the 0.194 and I can multiply it by 3, and that would give me 0.582 moles of H2. And then I have non-ideal conditions, 47 degrees Celsius, 725 for the millimeters of mercury. So I can use now PV equals nRT, and I can solve for volume. So in this particular instance, I would have the 0.582 moles. I would have the 62.4 liters times the millimeters of mercury per mole Kelvin. And I would have a temperature of 320 Kelvin. And I'm going to divide that by 725 millimeters of mercury. So again, let me just cross that out and rewrite it over here. That would be 320 Kelvin. Sorry about that, ran out of space. So if I take that, multiply it by 62.4, multiply it by 320, and divide it by 725, that gives me a volume equal to 16.0 liters of H2. All right, so that concludes our second lecture on the ideal gas law. We will do a third lecture covering the kinetic molecular theory, and we'll have a last one dealing with the last of our gas laws with Graham's law of effusion and Dalton's law of partial pressures. Please come to class with questions tomorrow.